Let's talk about reactions of alkyl halides. In particular, I want to look at the E2 reaction, and I want to look at the reaction of these two different alkyl halides. The only difference between these two alkyl halides is the stereochemistry at this center right here. In this molecule, it's R. In this molecule, it's S. You'll notice that I've color-coded my groups, so my methyls are green, my phenyl group here is blue, and my bromine is purple. And we're going to focus on this molecule first. I've got a three-dimensional model of it here that I can turn and spin and so on. And what you'll notice that I've left off of my planar molecule model here are the two hydrogens. One of them I've colored red, one of them I've colored white. So I should add those hydrogens because they are very important to this reaction. Now, critical to predicting the correct product from this reaction is recognizing that this hydrogen which gets taken by my base and this bromine which leaves have to be anti-periplanar to one another. And by that we mean that the hydrogen and the bromine have to be in the same plane and pointing in opposite directions. And they get that way because we have free rotation around this single bond. So we're going to rotate around this bond until we have the correct configuration. And that the way that I normally do that is to start off first by drawing my bromine and my hydrogen in the configuration I want them to be in. So I draw my hydrogen and my bromine anti-periplanar. And then I recognize that even though I've rotated around this bond, the stereochemistry at these two stereocenters has not changed. So this was R to begin with, so it's still R over here. And likewise, this stereocenter was also R to begin with, so it's still R right here. Now, if I look at that rotation on my three-dimensional model, what I'm going to do is take my model, and I'm going to orient it so that I can look down the C2, C3 bond. This is my bromine, this is my hydrogen. Those are the ones that have to be anti-periplanar. So let me highlight this bond and rotate around it until I get them anti to one another and periplanar. So now if I go and look, this is what I have. So this is the same representation I had over there. Actually, let me rotate it like this. So bromine going straight up, hydrogen going straight down, bromine up, hydrogen down. Now this helps us predict what product we're going to get when the T-butoxide, which I've shown here, takes this hydrogen, these electrons move in, and the bromine leaves. You'll notice in either this model or this model that one of my methyl groups is sticking out towards me, the other one is sticking back away from me. When I get my final product, they're still going to have that same relative relationship to one another. So in my product, where my double bond has been established, my methyl groups are pointing in opposite directions. In other words, they're trans to one another, just like they were trans to one another here. We can view this a slightly different way if we look at a slightly different version of this three-dimensional model. So this is the molecule product that we just looked at, or the anti-coplanar version of this reactant, I should say. And you can see the bromine going up, the hydrogen going down. And I want us to think about what happens when this bond starts stretching, this bond starts stretching, so that they start leaving. So the base comes and starts to take this hydrogen, the bromine starts to leave, and as that happens, this methyl starts to move up, this one starts to move down, this group starts to move down, and if I rotate this a little bit, I can drag this one up a little bit. They all start to enter the same plane. Finally, these atoms are gone. And what you can see is when this new bond forms here, these groups are in the same plane. And they are anti to one another, or as we normally refer to them, trans. I want to look now at my other reactant, which, as we said earlier, the only difference is the stereochemistry at this center. So this is my three-dimensional model of this molecule. You'll notice nothing has changed at this first stereocenter, but now instead of coming towards us, the phenyl group, which I've represented with this blue sphere, is going away from us. We're going to start out the problem the same way by drawing this molecule in the reactive conformation with the bromine and the hydrogen anti and periplanar to one another. So bromine up, hydrogen down, same plane. Keeping in mind that we didn't change anything at this center, the stereochemistry here and the representation here is going to be the same in the second example. And in going from this to this, we switch the stereochemistry, so the phenyl and the methyl group will be switched from one another, with respect to one another. Again, we achieve that by rotating around this single bond. We can view that rotation in our three-dimensional model. We want this bromine and this hydrogen to be anti-periplanar with respect to one another, so let me rotate that. So I'm rotating around that bond until my hydrogen and my bromine are anti to one another. Let's spin this around so we can look at it a little bit easier. And what we see in that conformation is that both of my methyls this time are facing towards me. You can see it over here as well, which means when I draw my product, they're both going to be facing in the same direction. They're going to be cis to one another. And you can see that they're cis. We can look at this process slightly differently using a different three-dimensional modeling system, different program. So in this model, my bromine and my hydrogen are anti and periplanar to one another. And I'm going to show this bond getting longer, this bond getting longer as those two groups leave. So my base starts taking this hydrogen, my bromine starts to leave. As that happens, this starts to move into the plane, comes down, this goes up a little bit, this goes up a little bit, this starts to come down. Finally, these two atoms are gone, so that when the new bond forms, and unfortunately turn that atom white, but the methyl groups are cis to one another, just as we saw over here.